Okay, everyone, today we're going to do two examples of integration by parts. And so for the first one, we have a linear factor times an exponential, right? And so I'll remind you of the integration by parts formula, right? We want to make selective choices for our u and then d that goes along with it, and our dv, and then it's v that goes along with it, so that this becomes easier to evaluate. Right? Now, when we're thinking about differentiating and anti-differentiating, we have to think how each one are going to go. Anti-differentiating a linear factor is going to give us a quadratic. That seems like it's worse than it was before, right? We want to differentiate the linear factor so it becomes a constant. Differentiating or anti-differentiating an exponential is not going to make our lives any harder whichever way we go about it. But anti-differentiating a linear factor is going to make it worse. It's going to give us a quadratic rather than constant, right? So it's in the wrong direction. And so by that logic, we want to make 3 plus 5x our u, so that when we differentiate it, right, then du is simply, 3 plus 5x rather, apologies, du is 5 dx. And that leaves us to fill in the rest of the stuff inside the integral, i.e. e to the 3x dx from dv, and then anti-differentiating that is simply 1/3 e to the 3x, right? That wasn't so bad. So now, by the integration by parts formula, we can, I'll use the blue color for contrast, we can equate this integral to u times v, so 3 plus 5x times 1/3 e to the 3x, so I'll do 1/3 e to the 3x times 3 plus 5x minus the integral of v du. Now this is where we see how much simpler our new integral is going to be evaluated. V du is 1/3 e to the 3x times 5 dx. 5 times 1/3 we can plop outside as a constant, and all we have left to evaluate inside the integral is e to the 3x dx. And that is a trivial integral to evaluate, right? And so our final product is going to be 1/3 e to the 3x, 3 plus 5x, minus 5/3 times the integral of this anti-differentiating is 1/3 e to the 3x. I guess we could do plus c for a constant integration, right? Good habit to build. And so, what could we do? We could even factor. There's a 1/3 e to the 3x in both of these, so we could do 1/3 e to the 3x times 3 plus 5x minus 5/3, right? And then minus 5/3 times c. If you want, you can call it plus d, right? Some other constant that's different than c, call it d, whatever you want to do. And then 3 minus 5/3, 3 is 9/3, so 3 minus 5/3 is 4/3. And so we can simplify this down to 1/3 e to the 3x, 3 minus 5/3, that's 4/3 plus 5x, and then some constant of integration. And that would be our polished final answer. Number 2, we're going to have to do this twice. So x squared, you might, if you've done enough of these, you're going to start to see that the pattern forming. We're going to have to do this twice, right, to get the quadrantal linear, and then once more to a constant. So again, we want to be selective about our choosing of u and dv. We don't want to anti-differentiate the x squared. That would make it x cubed. That's even worse. Wrong direction. We want to differentiate it, right? So let's let u be x squared, forcing du to be 2x dx, and then dv will capture the rest of the integral, cos 4x dx, and anti-differentiating dv to get v. We're going to get v is the antiderivative of cos is sine, so we're going to get sine 4x. But you have to consider the chain rule, right? And so we plot along factor 1/4 at the front, because you know if you were to differentiate it, if you were to differentiate v, you get cos of 4x times derivative of 4x, which is 4, cancel out the 1/4, and so you get back through cos 4x dx. So all of that to say, we can equate this integral by the integration by parts formula now to u times v. So that'll be u times v is going to be 1/4 x squared sine of 4x minus the integral of v du, so that'll be v du is going to be 1/4 times 2, so that'll be 1/2, and x sine of 4x dx, right? So you see the pattern. The x squared has now come down to just x, and so we'll need to repeat this once more. So once again, we'll need to do our for contrast. We need to make selective choices about our u and dv. We don't want to anti-differentiate the x. That'll bring it back to x squared. That's no good. It'll undo all the progress we've made. We want to differentiate x, and so let's make u be x. Now, of course, du just be dx, and then dv can be the rest sine of 4x dx, and that'll make v the antiderivative. That'll be negative 1/4 cos of 4x, right? And so now we can keep going, and so we can do 1/4 x squared sine of 4x minus 1/2 times, now this entire thing, right? This integral is going to be broken down, and so we'll have u times v, x times that, so that's 1/4 x cos, negative 1/4 x cos 4x minus the integral of v du. That means minus negative 1/4 will be plus 1/4 cos 4x, and then du is simply dx. And so this is where we wanted to get to. Now that integral with cos 4x has no other part to it, and so we can evaluate it. So in the end, we'll have this first term from the first step, 1/4 squared sine of 4x. Minus 1/2 times negative 1/4 means plus 1/8 x cos of 4x. And then we'll have minus 1/2 times positive 1/4, that's minus 1/8. So that'll be minus 1/8. The integral of cos 4x is 1/4 sine 4x. 1/4 sine of 4x. And then we can do plus c at the end, doesn't really matter. And then what can we do from here? So then we have a sine 4x and sine 4x. So we could do sine 4x times 1/4 x squared minus 1/32 plus 1/8 x cos of 4x plus our constant of integration, c. And we're done. And so this is nice and tight. We factor the sine 4x out of both of these terms, condense our final answer. We always want to simplify as much as possible because it's easy to plug into some computer program as we can, nice rule of thumb. And so there we go. Hope this helps. Thanks for watching. Have a great day.